Good morning, good evening, everyone. How you doing? So this is the presentation I gave at Reno Vice. I'm sorry if you guys couldn't make it. It was a really great event, really chill, had a lot of fun. But just gonna jump into the discussion. Um, yeah, see how it goes. Okay, so it's a general dive into it. Nothing specific or nothing. We're not going to get too deep into the math, too deep into troubleshooting. More of an overview of what it is, what it can do, and stuff like that. Would like to thank FrixX, Andrew, Eddie the engineer, 3D printers and a whiteboard, and Noob um, for help and for setting up the Reno Vice and for all the help they give me so I could give you guys this presentation. So who am I? My secret agent name is Reth. It is based off a D&D character. I got tired of making new names, so I have Reth 1 through I think 15 right now. I have several degrees. I work as a patent examiner for doing semiconductors. I am not a mechanical engineer. So a lot of this stuff that I've learned either in my previous job experience or just figuring it out and obviously talking to Andrew and Fricks a lot. This is my CYA disclaimer. Since I am a patent examiner, I will be referencing certain patents drawings in here. So obviously nothing I say is the word of the agency. This is on my own personal view and stuff. So I used to work for ASML. They are the largest photolithography semiconductor equipment manufacturer, I believe, in the world. They are doing the EUV stuff. So if you guys are familiar with TSMC and their top of the line, TSMC and Intel and Samsung and Micron, anybody that's doing state of the art chips right now, the very latest and greatest, they're using not this device here, not this printer being shown, but they're using an ASML twin scan EUV printer. I think those things are upward of $150 million plus at this point. Size of a bus, and that's just the printer. Support equipment is just as big, and it's usually in the basement. But these are the tools I worked on. These are called PAS 5500s, and just to kind of show you some of the vibrations that they had. Um, that's okay. So this right here is your wafer stage. That right here is your reticle stage. It's like a giant camera, right? Giant camera with a laser beam. It's either argon fluoride or something else. 193 or 248 nanometer. This is showing you a 365 because it's got a culminator here. So that had a mercury arc bulb in it. But basically, these things on the wafer stage, it's on a giant piece of granite. It's an air bearing, so this thing is floating basically on a giant piece of granite with linear motors like the Magneto X, except these ones were a lot faster. It also has 3 air bearings holding. So this is on a cradle basically, and it's got holding up the granite and everything are 3 huge air bearings to basically isolate everything. You can see all these wires. Every time I tell you guys, if I've given you help and I've said you want a lazy river or a snake-like, these here wires here are going from the isolated area, which is inside the chamber, and it's actually holding up the lens, and it's also holding up the reticle stage to the outside world. These wires here are doing it, and they're going in this pattern to reduce vibration from all the panels that go on this thing. You can see the panels, everything on the outside to the inside. So this is why you want a lazy river. You want to minimize the vibrations coming into your measurement, or in this case, it would be this thing. All these pictures were taken from the web in ASML. There is a little thing right here. It is the worst thing ever to fix. And this is kind of my experience working for ASML with resonance. It's a 2-bolt system where 1 bolt is a cam, so it can move it left and right, up and down, and the other is a set screw. This thing is basically it's like our hot ends, where it's just basically floating there. You could, if you push on it with your finger right here, it'll vibrate this way, and this thing will cause, you could see it. You could see it on the test, and it will cause issues that you have to solve because that's a vibration that you don't want in the system. Much like our umbilicals and other stuff. It's so this was my experience with it, and it is horrible to fix if you get it wrong. You're talking a day or so if you're not very good. Like I wasn't at fixing that. So we have a simpler system, but in many ways it's more frustrating. As you know, Voron is a community-driven project. We're not throwing money at this thing like crazy, right? So the ASML printers, they had characterized all the vibrations, and they could tell you effectively where to look for the problem in like an order of 1, 2, 3 kind of thing. So we don't have that. We don't have hundreds of millions or millions of dollars to throw into categorizing the resonance, figuring every little thing out. In addition to that, our printers aren't built on an assembly line. If we had an assembly line, we could figure that stuff out too. If every printer was built the same with the exact same parts, and we started getting issues, we could go back and figure that out. We don't have that. All of our parts are, as we get them, they're not precision parts. Therefore, every single one of our printers is effectively a unique printer, although we all share common design features and common aspects. Because of how we build it individually, what we choose to build it with, and how we printed our printed parts, every printer is different. So there will be some variation in all of our resonance testing. And it might not be huge, and it might not be big, but it'll be some variation. Thankfully, though, at least most of the major parts, they do react the same, right? So we know certain things are going to react, and they're going to react the same. Other gantries besides Vorons do not necessarily react the same. We've gotten other printers in the Voron channel, which is fine. I'm happy to help. I would just ask that you let me know that it's not a Voron. But even though they're Core XY, they are designed differently, and their parts are different, and they're going to vibrate differently. So I'm looking at a Voron, I'm looking for a very specific pattern, and a certain kind of fingerprint, if you will. Other printers are not going to share that fingerprint, and that becomes an issue with trying to help you in those other printers. I will kind of see what I can see and maybe give you some pointers, but you're not going to get the same level of support if it was a Voron printer, just because the frequencies are going to be different. So what is resonance? Well, it's the natural frequency at which an object oscillates if you apply an outside force, right? So if you push something and it starts going, a cup, a glass will be this good idea, right? So crystal glass, you get your finger wet, you go, whoa, and you make the glass sing. It's going to be, that's its resonance frequency that you're hearing. You're hearing the wah, 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 right? The glass singing. So that's what resonance is. Damping ratio is a loss of energy that's happening, so the decay of the oscillations. Voron printers, our natural range, or normal range I should say, is about 0.4 to 0.06. This is important later on when we set it input shaper in printer.config. Clipper sets the value, kind of defaults it to a 0.1. It's kind of a safe value for everyone, but they do allow you to change it. This is a very standard, this graph right here, it's a very standard Clipper graph, right? So, as you know, we have two options. We have Shaketune and we have Clipper, standard Clipper resonance. Shaketune gives you a little bit more information, and it also deals with this damping ratio, where standard Clipper just defaults to 0.1. So why do we need to worry about this resonance hole? Who cares, right? Why is it such a big deal? Effectively, it allows us to go faster with improved quality of prints. Now, you can go too fast for the input shaper to correct, and you'll see that with like the speed benchies, and things aren't coming out right, and maybe not resonance. I'm sure there's resonance in it, but it is basically canceling out the ringing due to the vibrating head of the tool head. And so if you can cancel that out, you do lose some stuff. Um, you will get smoothing in your prints. It is a byproduct of the shaping process. So you will get smoothing, which means easiest way to explain it is the back of a benchy. There's lettering. So the more you try to correct it with the more extreme shaper, we'll go back. Well, I'm going to go over all this, but I'm talking about it now. So you got 5 levels of shaper. ZV is the least amount of shaping, which will get you the least amount of smoothing. 3 hump EI is the most drastic one, and it will give you the most smoothing. So that's the trade-off on going using this, is you will get some level of smoothing. So what affects the shaper measurements, right? When you want to know what's going to do it, here's a list. Pause it, take a look at the list. I'll give you the short thing. Everything in the motion system, everything on your gantry, and if you're, anything on that gantry, anything and everything is going to potentially affect your input shaper measurements. So if you don't on a 2.4, if you don't home in QGL and your gantry's racked, or your gantry is, it's racked because it hasn't been QGL'd, it's going to affect it. Center of gravity. So a lot of people like designing their own tool heads. If you design your own tool head, you better get that center of gravity right, or you're going to be affecting it. It may be the coolest tool head ever, but if your center of gravity is either too low or too high, your tool head's going to rotate around the axis when you start accelerating, and that'll show up. Even how you connect the ADXL, the measured sensor. So if you use really heavy wires and you have that thing kind of just falling right off of it, it's going to affect the measurement because now you're pulling on things. You're pulling on the tool head. So basically anything and everything will affect this. Some will affect more, but it's a de minimis more, right? So what is it doing, right? So this is my first patent. You guys can look this number up. It was issued in 1997. There's the number. Google patents, you'll find it. And this is basically input shaper in a nutshell. So this is our original signal. So this is with no shaper. Let's just assume this is what we want the tool head to do. We want it to move, accelerate, slow down, right, and all this stuff, right? Well, what is this shaper actually doing? It's depending upon the shaper. It's going to put in certain impulse pulses at different times into the shaper graph, right? And then this leads you with this. So it's going to A1, it's going to turn into this guy here. A2 is going to turn into this guy here. Your resulting shaper, you want this. This is going to be your movement. What you get at the end is this top one, right? This shaped input. You're going to get this. So they look very similar, right? But they act different. And this is what happens to your tool head, right? Your motion system when you do this. So ZV will give you 2, MZV will give you 3 impulses. EI, I believe, gives you 3. 2 hump EI gives you 4. 3 hump EI gives you 5. And they'll create different signals to get this in there. So that's what it's actually doing, and it's doing that to the motor drive, to the motion system, and then relates it to the motor drivers and then to your motors. This is about as heavy math as we're going to get. So what values are important to the input shaper, right? Well, basically it comes down to your frequency, your main peak, at the frequency where it's at, and then your damping ratio. So if you get that frequency and then the type of shaper, right? So we'll walk. This is MZV. This is in Clipper. You can actually go check it out in their GitHub, and I forget the file that it's in. It's like shaper defs, I think. It's in the Clippy extras, I believe. So it's going to calculate you these 3 A values, right? Which, if you remember, are the 3 impulses into it. So what do you, EI is over here, so EI is also 3. What do you need, right? Well, you need the damping ratio. Then you need the shaper frequency. And it calculates everything else. So this DF value is based on damping ratio. The K value is based on the damping ratio. This TD value is shaper frequency. It then takes these in here and puts them in here. So you can see A1 impulse is always going to be this. It's always going to be the same one. But your A2 takes in K values. And then the A3 takes in K values. I didn't put the times in, but the times, well, here they are. Times taken TD. So that takes in your so when it's going to hit these is based off of your amplitude, or is based off of your frequency, where it's at in frequency. The A values, your amplitude, is going to be based off your damping ratio. There's EI and MZV are very similar, but they have slightly different maths. And there's a VTOL, which is a vibrations tolerance, built into EI. EI is kind of it's known already. MZV, I believe, was developed just for Clipper. There is the one they had before was called ZVD or ZVD. I believe it didn't show too much of a difference between EI or ZV. So they created this one. It's kind of in between the two, and you don't see ZVD anymore. So that's the math it's doing, right? So your times are based off of your frequency, and your amplitudes are based off of your damping ratio. This takes us back. We're going to go back. Let's see if we can get back to here. And this is why the damping ratio is important. An accurate damping ratio is important to put in because it's going to determine the amplitude that is the impulse, the amplitude of the impulse based on that. So when Clipper defaults to this one, your amplitude may be a little high. This gives you a more accurate representation. Okay, so as I said they're applying the A and T values to each movement. Why can we do this? We can do this because we know everything that's going to happen. We know the future effectively when you start a print. We got G-code. G-code for these machines, it doesn't really know what you want to do till it reads the G-code. So we know everything. So Clipper can pre-calculate or calculate as it needs to all the different shapers, and apply the shaper before the movement happens or be ready to apply it. There's no surprises in what it's doing. It knows because of the G-code. We're going to take a veer off into TMC Auto-Tune. So what is the difference, right? What is the difference between Input Shaper and TMC Auto-Tune? So the short of it is Input Shaper takes care of your accelerations, right? It tries to take care of the resonance, the ghosting, the vibrations caused by the tool head when it accelerates and decelerates. TMC Auto-Tune tries to effectively auto-tune your TMC drivers to get rid of motor vibrations. So they're both getting rid of vibrations, but they're getting rid of it for different causes. It's, as I always say, this is free performance right here. That's free performance to install that. And Andrew, this is where Andrew comes in. Andrew created TMC Auto-Tune, and basically he has read the manual, created the code up, and all it takes is your motors into account. Everything else is kind of read in from your printer config, right? Your speed, your currents, and all that jazz. And so it will set appropriate values or good enough values, let's say, to clean up any sort, to help you get rid of any sort of motor noise. So I'm going to try to do Andrew justice here. I don't know if I can, but here is what it's doing. These are your TMC drivers. Okay? This is its on state. Basically, it's 4 transistors in a circuit with a sense resistor of some sort. This is your on phase. Your current's going to go up and straight down through your this L is your motor, and it's just going to go through, right? It's going to drive that motor. Then you have a fast decay where they close the path, or the path goes in the opposite direction now, right? So it's going to go this way. Current's going to go that way, and bleed out the system. Then they have a slow decay where they close the 2 bottom ones to ground. They open these up, and it kind of just cycles. I believe that's how it goes, right? Open, close, 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 yep. And it's just going to cycle through and burn out all the extra current through there. This is what it looks like. you're going to go, you have an on phase, a slow decay, fast decay, slow decay, on phase. You can control the shape of this graph. Um, I will say that these pictures came from TSMC's patent, and their patent explains it just as clearly as their data sheet on actually how to control every single aspect of this, and it's not very clear. Um, it's you would expect them, because you can control this point, that slope, and they don't necessarily tell you how to control this whole thing. There's still some secrets in their data sheet. It's there in the chip, and Andrew has I think he found most of them now, how to control most of this. It's just the documentation is not clear from TMC. But this is your motor driver, right? So when you're asking it to do movements, these are the movements. These are the phases of the movements that it's going through, and this is what you're controlling with TMC AutoTune. So now we're going to use an example for one of my printers. This may get a little convoluted, but hopefully you guys can bear with me. So I've kind of done this two ways. I ran the same test. This is standard Clipper, and this is Shaketune. So there's a lot of writing here going on, but we'll start here. This one A belt in Clipper is known as 1, -1. B belt, this is for core XY. Deltas have a different naming structure. Deltas have a different naming structure, and this does not apply to core XZ or bed slingers. You cannot run belt shaper on a bed slinger. They don't do Z. Clipper does not do Z, so you can't do an XZ or belt slinger bed. This is only for something that has an X and Y motor. So the orange is your A belt, the blue is your B belt. Clipper is just going to tell you the axis here. Okay. Shaketune over here will tell you the belt and the axis, so you just see it's that, but they remind you of this. They all line up, and everyone's happy. Well, yep, everyone's happy. So the power spectral density is how much energy the resonance has. Generally, we don't concern ourselves with that. Like, it's not necessarily the best to compare power spectral density or PSD from one graph to the other. The only thing you really want to look out for here, if it's really low. And really low is relative. Obviously, if it's if it is 1e to the 2, you got a problem. 1e to the 3, potential problem. 1e to the 4 or higher, you're fine. You're going to be fine. It doesn't need to be 1e to the 6 or 1e to the 8, and if one is greater than the other, on these graphs, it doesn't really matter. So what does belt tension tell us? Right? All it's giving us is relative belt tension. How tight is A belt to B belt? It's not giving us absolute tension at all. So for absolute tension, you would use something like the PFmakes tension tool, where you actually physically measure the belts. But another way to think of it is once you get the belts in with the PFmakes tension tool, you will then use this as kind of a fine adjustment, because you know the belts are about the same because you measured them. You don't know how similar, because the PFmakes tension tool has inaccuracies. This is your fine measurement. This is where you can see the belts are. What we're looking for is a single peak. A single peak. We will settle for a double peak on Vorons and most other Core XYs, I believe. This here is coming from reason you get a double peak is going to be your XY joints. So if you've got two peaks there, it doesn't matter which one's higher, which one's lower. It's fine. That's because your XY joints are coupled together. Your XY joints couple your X-axis and your Y-axis together. So one of these, generally this one here, is going to be your X-axis. That's your Y-axis for these belts. For this graph. It does not mean this is your x-axis for input shaper. It just means for if you were to measure it, this is going to be your x-axis in the belts, because the belts, this test, it moves. Let's go back to your tool head. Let's go back to this. Okay, x is this way. I'm sorry, x is this way. Y is this way. Your A motion, I believe, is this way. It's a diagonal. Your B motion is another diagonal. So belt shaper, what it's doing is it's moving these guys in diagonals and measuring the resultant resonance. So it's measuring the, you can think of them as the 45s. Because this is, one is 45, one is 135 degrees from the tool head as your center point, as your measurement point. So that's why they're not, you can't necessarily use them for X and Y, like this, but the double hump is coming from the joints. Because as you can see, both joints, here's your A belts on that bearing, and your B belts on this bearing. So that is why you're going to get double humps because of the coupling. It's not bad or good. So that is what this is telling us. Now, what has Fricks given us extra? Fricks has given us this runway here, and basically this is like your good zone. You get in the good zone, I call it a flight path or runway, by having your belts at the same frequency and same amplitude. Obviously, my belts aren't at the same amplitude, right? And he tells you that. He tells me, oh, my alpha's 37% difference. You know, okay. If you have to choose, the best is a mirror copy, one on top of the other. That's the best. That'll get you right in this green zone. If you have to choose frequency over amplitude. You want the belts to be vibrating at the same frequency. You don't really care if one belt is here and one belt is over here. They're not vibrating at the same frequency. If you have to choose frequency over amplitude. So 0 on the main peak, 1.2, I'm happy with that, obviously. In Fricks X and Shaketune, do not look at this number, because you could have ugly, ugly graphs where things are going all over the place, and it's going to say 100%. All this number means is if you take the totality of one signal and I put it on the other signal, how close are the signals? They're 96.1% close. All right. You can tell. You just need this graph. And you need this flight plan to see, okay, am I good enough? Yeah, you're good enough. If you're on the same frequency, the points will be here. If you have different frequencies, the points will be on other sides. And then if you have different amplitudes, they'll start diverging this way, I believe. So, how do we fix this, right? You guys want it's always, what do I do? I see this, what do I do? Okay, so we look at this a little bit more. You want the points to meet. Obviously, you want it there, right? We talked about that. The higher frequencies, so basically, let's say this range here, they have less impact on the prints. It could indicate a mechanical issue. So I said this is not mechanical troubleshooting. I just said that. However, caveat, it could indicate it. It could also be nothing. This is why you run input shaper afterward. So this is different than this. It's because it could be, my belts could be slightly off tension. I could have potential racking. Very slight, but once again, 0% delta on the frequency of these two, I'm happy. This could happen right here because the alpha is low, right? So it's not up. If it was up higher, it'd probably stretch this up. Not a big deal. This is some junk. It could potentially show up all this. So this is your angles, right? This is your 45s and your 135, your angles. It could. If this is really bad, you could potentially see something on the angles. Potentially. But once again, you can't really rely on it. You'd have to do a print to see. So that's reading this guy. Your X input shaper. So let's see. Can we blow this up some more? Let's get it up higher. Boop, boop. Boop, boop, boop. Can you guys read that? I don't know if you can read that. I'll have to tell you what it is then. Let's see. So this is Clipper, Shaketune. One of the biggest differences you are going to see, if I could make this bigger so that you could actually see. Let's see, let's move this guy over. Let's move this guy over. Can we get any bigger? Okay, we only care about this right now. Okay. This is the exact same machine, and this was run one right after the other. This thing you're going to see is MZV is reporting 0 vibrations, and Clipper, it's reporting 0.4 vibrations remaining in Shaketune. Why is that? It's the damping ratio. That's the damping ratio. That is your resulting vibration. If you remember, Clipper's using the 0.1 default. Shaketune's using 0.066. Right? It's actually taking this number, putting it back into the shapers, and giving you actual values here. What else does it do? Well, Clipper says you can run at 15,300 for MZV and X, where Shaketune says 14,700. And you know they kind of track, right? We're not too much, but right there we got a difference. Right here we got about 300. The reason for this is the damping ratio, and I would argue that this is a more accurate representation of what the shaper can do. If you use this, are you gonna, all of a sudden get a whole bunch of noise and by ringing and ghosting? No, you're not. You're not. It's just not as accurate. That's all. I prefer this one because at least I got know where I'm at, and this one's you're a little off. I have yet to see on Shaketune 0% remaining vibration on MZV. The damping ratio is there. However, caveat with that, Frick states that if you have less than 5% remaining vibration, it's okay to use it. Another caveat, you see that ZV has 2%, so am I saying you can use ZV? No. ZV is too narrow of a shaper to use. It's only really canceling out that main peak, and during the course of using your printer and actually printing, your frequency may diverge off of that center peak, and you'll start getting ring, and you're going to be like, why am I getting ringing? I'm using ZV, and my Excel is below the 2500 or the 2400, and it's because your tool had moved out of that frequency range in its course of travel. Just to give you, we're going to go backward. We're going to keep doing this. When this tests this tool head, it's only moving like a millimeter, 2 millimeters in a direction, right? So you could be fine right here going do, right? But when you're printing over here and over here and then moving around, the tool head may be experiencing different vibrations from different positions in its area. So you want a shaper that can take care of all that potential unknowns, which is why you don't want to use ZV. You want to use MZV at the least. EI and MZV, we're going to get into the next slide, but there's not. You're fine either way. Okay, so let's try to. We got to shrink this down now. Okay, we're going to take a closer look at Shaketune. Whatever I say here will also apply for Clipper, except for the extra stuff as we told you. On the left, let's see, is it there on the left? On the left, you've got your Clipper and Shaketune only work off the combination of signals. So the shaper they give you is based on X, Y, and Z. The main peak here you see is the combination of signals. So you have 3 axes in your 8XL accelerometer. All 3 are combined. That's the big peak. Generally, what you will have is the axis that you are testing will have the largest peak. So in this case, it's X, which is actually accurate to be read, and that's the largest peak. And all this other stuff is kind of there. You don't see any Z or Y. It's all buried here. Hardly anything. That's what this is telling you. This is your... Now these 3 peaks, X, Y, and Z, because Clipper doesn't care, These are just for your representation of the different axes to help you, but they aren't necessarily accurate. Sometimes your Z can be your Y can be your Z, your X can be something else. You kind of have to look at it and say, okay, what do I think this is? What axis was it working on, and what do I think this is? There is Clipper does have axis map, which will allow you to change all three of those, but you've got to figure out which one's which. Then you have ZV applied, and with MZV applied. So those are these two signals. It's telling you this is what your resonance frequency looks like now. That's the shape of it. If you apply ZV, we're going to give you this light blue. That's going to be your resulting vibration. If you use MZV, we're going to get you a little lower, right? And you can see that here because you have the resulting vibration of 0.4, which is that, and 0.4%, which is this, right? EI, you'll get to if you're a Voron printer and a Core XY Voron printer, you should be able to get 0% EI. This is why in the resonance channel, our goal is to get you 0 EI or less than 5% MZV. Those are both attainable goals, and that's why we chose them. So then Fricks has added some other things, a relax region, which is down here. If you see this thing in here, just relax, just chill. That's cool. It's too low of an amplitude to affect anything, right? Like that thing right there, just chill, just don't worry about it. Then you got a warning region, which is right above that. That may or may not affect your graph. So I got this little thing here in the warning region. Am I worried about it? Not really. Not really. The shaper's doing a pretty good job of taking care of that. And when you compare it to that, it's de minimis. So this is what I was talking about, the PSD, power spectral density. Just you got to watch out for the really low and the super high. All right, so you can see 1e to the 5, it's fine. It's fine. 1e to the 4, probably fine. 1e to the 6, 7, yeah. 1e to the 9, even 1e to the 8. You might want to start looking at stuff like, why is it that high? So that's just kind of another thing to look at. Shaketune also gives you square corner velocity. It allows you to set that as a variable in the test. Why is that important? Because your recommended acceleration is based off of square corner velocity. So if we go back here, that's another thing I forgot to say. Both of these, this is set at square corner velocity of 4.5. This one takes it from your printer config, which is generally 5. There is a difference there too, and that will affect your accelerations. Because it's part of the calculation. It says what's your square corner velocity. Will affect it. Now, do not get crazy with this. I've seen guys putting in 100. You will break the algorithm. It will give you, generally, the higher you go with this, the lower your accels are going to be. So if you give it 100, don't be surprised to get accels of 0. You have effectively broken the algorithm. 25 is sometimes too high. So what is square corner velocity? Square corner velocity is how fast in velocity, right? So millimeters per second. How fast you're going to take a 90-degree turn. The lower it is at 0, it means you're going to stop at the 90, and they are 90 degrees or greater. So 5 millimeters per second says you're taking a turn at 5 millimeters per second. 100 millimeters a second says you're taking a 90-degree turn at 100 millimeters per second. So what's so wrong about putting this so high? The higher you put that, the more rounded your corners are going to be. If you want sharp corners, then you need to set it lower. A good rule of thumb is you take your perimeter accel, whatever acceleration you set for your perimeter, and divide it by 1,000. And yes, you have to set it something to run this test, and yes, you need this test to figure out your perimeter velocity. But a good rule of thumb is perimeter velocity divided by 1,000. So if you got 5,000 on your y axis for accel, it'd be 5. If you've got 3, 3. You can always go up. The only negative, as I said, is smoothing around the corners. Um, and you can always go up, but it's a good rule of thumb to get nice, crisp, sharp corners, and then you kind of go up from there as you test. Shaketune also allows you to set a max smoothing. I have never needed to do this. I mean, look at these smoothing values. It's 0.03 all the way to 0.05. I don't know if you guys can see that. Probably not. But it's already really low. Especially when you put in this damping ratio in. It's Vorons have pretty good smoothing characteristics. Very low. Accelerations per hertz. You can change this in Clipper. It is how much energy you are putting in the system for each hertz. So the way this test works is it hits your tool head at every single one of these hertz, 1 hertz increments across from 0 to 200. And how much energy is it putting in there? It's putting in 75 millimeters per second squared per hertz. That's how much energy it is. The higher the number, so they default to 75. The higher the number, the more energy. Sounds great. More energy, I can get crisper graphs. And you can. The negative of higher energy, so like I'm talking 1 over 100, right, is that you will start drowning out or start hiding the bad stuff that's happening. So I've seen it where people have bad graphs, and they're like, that's a bad graph. I'll just increase this. And all of a sudden they have a decent graph. That bad stuff did not go away. It's still there. You're just masking it. You're hiding it. No bueno. 75 to 100 is plenty for these machines. So the next thing are these lines here. All these dashed lines correspond to every single shaper. Excuse me. Every single shaper that we have. And what you can see, so we'll take ZV, which is this blue line. This is actually the shape of the ZV shaper. And if you take that shaper and you do a 1-for-1 subtraction, so I'm going to subtract this from that, boom, lands me here. And you do that, you can see where this shape comes in. This is the greatest amount right here. This peak here is the greatest amount of subtraction. It's going to take that out. If we move to MZV, which is the next one here, it's doing kind of the same thing, but it's a little lower than ZV right there. You see that? That is now why this is so much lower, because it's subtracting more from the signal. And then you can get a little here, which takes it down a little further, a little quicker. So MZV goes like this, and then you have EI, which starts here, and it goes here, like this. Then you have 2-hump EI and 3-hump EI. You want to stay away from the humps. Stay away from ZV, stay away from the humps. It's just too much, it's too much smoothing, right? And okay, let me rephrase. For X, generally for X, you can use the humps, because the biggest thing is the smoothing, but this frequency generally is much greater than the Y frequency, or greater than the Y frequency that we will use as our actual external perimeter accelerations. So for X only, you can go ahead and use the 3-hump if this value, this last value here, this acceleration, is greater than your Y acceleration. So you may have a little bit of a nasty graph on X. You can solve it by switching to a different shaper, a lower shaper, just as long as that's taken care of. That Y-axis is still the slowest speed. Oh, we got even more. I really broke this down, didn't I? So those are our shaper lines which we talked about. So let's talk about the shapers. This is your shaper. It's right there, ZV, MZV, 3-hump, EI. They all are short for something, and I don't know what they're short for. I think it's 0 something or other. 0 vibration. I don't know what that one is. I don't know what that is. But anyway. Then you got your shaper frequency. So this is the center point of the shaper frequency. You can see that it keeps ZV is 72.6, which Fricks gives us our, so this is actual, right here, this axis frequency profile. This is our center frequency, the top peak frequency, and this is the damping ratio. The damping ratio generally is the same here and here. But this is the center point frequency of this graph. ZV will try to cancel out 72.6, which is just to the right of it, just the side. ZV goes back a little bit, so it's like, I'm going to go back this way. EI goes well ahead, which is around here. 2 hump EIs over here, 3 hump EIs over here. And that's just the center point of these shapers, right? So what they're trying to cancel out. Then you have VIBR, which is vibration remaining. And this is tell you how much, this is a guesstimate. It's the calculation. It's saying, if you use this shaper, this is how much we think you're going to get. Then we have the smoothing, how much smoothing they think the shaper is going to apply. And this is the calculated max acceleration based upon the shaper. Now this is a, I talked to at Reno Vice after this presentation. I talked to Kevin of Clipper, and it's not necessarily a max acceleration. It's a max, I think it's a max recommended acceleration. You can go over this, right? So it's a suggestion, right? It's not saying that this is the max. It's a suggestion. You can go over it. Now, there's no guarantee that you will necessarily be canceling vibrations past this recommended acceleration, but there's no harm in going over, right? It's one of those things where you're going to have to do prints. You're going to have to see how far MZV or EI is going to take you. It will fail at some point. It will not. There will be some point where it can no longer correct the resonance, but you just going to have to test it out. I stick with this number. I need a number when I'm doing my print profiles. I need a number to put in there. I use these numbers. I consider them maxes in the way I work. So these are your calculated performance things. The shapers, this recommended low vibration, all these shapers, they don't look at your graphs. So if you have a really crappy graph, but it has a high center peak, it's going to recommend ZV. You could have a graph with junk going all over the place, but then boom, really high, super high peak, and then down. It's going to say, oh, ZV will cancel this out. It doesn't know that super high peak is probably some sort of mechanical issue. It doesn't know that. So don't rely on these numbers here, these recommended performance and low vibrations. Look at the graph and see, does it look right? Does it look similar enough to this guy? And then you can go from there. Damping ratio, it's the width of this peak. You can also think of it as the width of this peak. Fricks has stated it's using the half quadratic gain method to calculate the damping ratio, but it's effectively the width of the peak. If you're over 0.6 in X, you probably have an issue in damping ratio. You could have a perfect graph, and if it's saying, use 0.9, there's probably, it's up to you whether you want to investigate it. It's probably going to be fine, but generally we're in the 0.0, we're in this range here for our damping ratio. So it's another little thing, and it's up to you whether it's worth it or not. It may not be worth it. So, yeah. Why input shapers? So why does mine look like crap? Doesn't really, right? It's all in the war. If we go to here, it's giving me Excel, you should go, okay. Alright, so I'm trying to remember what I wrote. We're going to do this. Your accelerations, when you're looking at this chart, if you want to know if something else is going on, another thing you can look at is your accelerations. Your accelerations should only go down from ZV to 3 hump. What you see here is it's 7,900, 55, 4,100, 4,800. It swapped up. It moved up. And then 4,700. This guy should not be there. It should be higher than 4,800, lower to or equal to 5,500. There's a problem. What is that problem? I'm glad you asked. as I answer my own question. Let's get this. This is the problem. That's the problem. Boom, 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 boom. That's the problem. Now it's in the warning range, and that's what's causing it. How do I know that? Because I found the problem. Am I going to fix the problem? Probably not. Probably not. No, it's not worth it to me to fix it. What is the problem? My X carriage on my X linear rail wobbles. It's when you take the tool head. Let's see here. Boop. So we'll look at this. We'll call. Let's just. We can undo this. And you have your ball bearing there, and then you'll have. What do you have like this? Ching, 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 ching. All right. This is my linear rail. This is my linear rail carriage. I cannot spell with this. And then here we have, we'll have Mr. Toolhead. That's a nice box. All right, Toolhead. And it's held together with screws or something. This piece right here. Can we go to red? Let's go to red. This piece right here is rotating this way and this way. So when I move the tool head forward, the linear rail carriage goes backward. When I rotate it this way, actually I gotta rotate it this way. Tool head, carriage rotates. So this carriage is no longer fixed. That's what's causing this wobble right here. This right here is this. And how did I solve that? I just rotated the tool head, took a look. Everything else looked good. I wasn't seeing anything. So just rotate it. So what's happening here? What is this telling me it's happening? This right here. How do I know? Okay, we'll do some troubleshooting. How do I know? Let's get rid of all this. Can't get rid of it anymore? Okay, so we'll do this. Bye-bye. Not all of it. Bye-bye. So, they're both the same. Well, we got a clipper here. Let's get bigger. How did I know? How did I know that there was something rotating? Right? Well, let's see where we're at. This right? Oh, that's no bueno. That's no bueno. We're gonna go back to red. Sorry guys, back to red. This right here. This is why. Right here. Well, there we go. Right here, right above the light. Oh, too far. Right above the light blue line is Z. So where do we see? We'll get the green out. So we see Z over here. I'm over here. We see Z over here, and it's going up like this. All right, and then it shoots up like that. Something at this frequency range, so probably about here to about here, centered around probably here, is vibrating in the Z direction. But it doesn't vibrate in the Z direction, right? Because everything's fixed. So nothing's moving up and down. What this actually is rotation. It is RX. Where are we at? There we are. RX rotation. Rotation about the x-axis, which looks like z-axis from a accelerometer. Because it's actually moving, right? So the tool head's moving in that plane. It looks like it. This is what we see. So that is why I knew something was rotating. That shouldn't have been rotating. I'm giving you I'm playing a game here, but probably smaller schools are retying or umbilical or new linear rail carriage. I'm giving the hints, the secret. It's the linear rail. So that's how I figured it out. So that's I looked at that and I didn't see. I mean, it could have been my umbilical. Could have been any one of these things. But once I rotated the tool head and saw that the carriage was moving, that's what it is. I'm not going to fix it. So, we have more than the ADXL. We can use an LIS2DW. Do not use this accelerometer, please. Why? It has a internal 400 hertz non-bypassable filter on the signal. Well, what the hell does that mean? So our signals go from, we measure basically from 0 to 200 hertz. In order to measure a signal, you have to sample that signal at double its frequency. I screwed this up at the Vice meeting. It's the Nyquist, I believe it's Nyquist theory, or the Nyquist theory. Twice, so you have to sample something twice as fast than what you want to sample. It's at 400 hertz. Why is that a problem? We're only going to 200. It's a problem because we're not getting any of the resonant frequencies, or the I'm out of words. You get the main frequency, you got 0 to 200, right? We want the other frequencies that pop around, and they are called, it's going to come to me like 30 minutes later. Harmonics. Thank you. We want the harmonics, because generally your main frequency just gives you amplitude, right? That's all it's really telling you. You want the harmonics to get a better shape, right? So these are examples of LAS2DWs. They're not all made the same. You can get a really bad one with this whole disco light show, You can get that one, or you can get this little laser club show. You get that. Not, okay, well, that's only in the spectrogram. It's not really affecting anything, but it is. Really bad ones will get you this. This is not real. That looks like binding. It is not real. It is the cause because of your LIS2DW's bandwidth. And this one's slightly different. Also, it puts an offset to it on this entire graph. There is some version of this graph that's moved up in the rest of the so you have the entry level, right? So we'll say, what happened? What did I do? I moved. Okay. You have 0 to 50, right? And actually, it's not even 0 to 50. It's 0 to about 25. It's about this range. If it does it, it's going to do that. But then it puts an offset on this whole thing. How much is that offset? I got no clue. I don't know. But you can't trust any of it. There are some that say that, yeah, you can still trust the graph if it looks like this one over here. Let's get out of this. If it looks like this one, you can trust it. I don't. I just don't trust it. You don't know what that offset is. So is that the true peak? Is that the real height? How high up is this? Should this have been in the warning range that I don't have to worry about it? Or is it something I'm about to chase? From a troubleshooting perspective, do not use it. There is no way to turn this thing off. It is hardwired into it. There was talk about how to, maybe we can use a different power mode to bypass it. It is non-bypassable. It's aliasing. And that's because it's not sampling the frequency. I believe the ADXL samples it at 1600 hertz. And that's why its graphs look the way it does. So, take it for what it's worth. So then we get this vibrations profile. This is Shaketune specific. And what does this tell us? This tells us the motor frequencies and the motor speeds. So as I stated earlier, way back when, 4 hours ago, input shaper is used for acceleration. Vibrations profile is used for your motor vibrations, for speed. Excuse me. How do you use this thing? Okay. This is kind of what you want. You want a iron cross or a cross, regular cross, or something like that, where the symmetry is 100%, and you got your angles 135, 45, right? These are the opposites of them. That's what you want to see, where that's going to have the least amount, because it makes sense if you're, like as Ellis has said, Ellis from Ellis Print Guide that we all know, if you want better graphs or print at better speeds, you print on the angles, you'll have less vibrations. And this data backs that up. So yeah, you're going to get less vibrations on the angles, on the 45s. Polar heat map, it's not as useful for me. Vibrations heat map. What do you want to see here? You want to see all orange, all the same color. Why? It means that your vibrations are evenly spread out throughout the machine. Yeah, your the light, the really bright stuff, those are the main vibrations. Where they cross, like here, see peak 3, they all cross. You get a whole bunch of vibrations crossing. Boom, peak 3 is high, right? Oh, some more, boom, there. You want this thing to be all basically orange. With you're not gonna get rid of these little like jet engine things or whatever, or, angel wings or whatever you want to call them. You're not going to get rid of them, but you want the whole thing orange. That means your vibrations are basically steady throughout the thing. You're going to see, some of you will see black here. Not ideal. It's acceptable, right? I wouldn't go, buying new motors over it. If you start seeing black on this side, though, chances are one of your motors was not working right. I would rerun the test. So what do we got? We'll start at the top, and then we'll go to this organic and structural thing. The top. If you have TMC Autotune enabled, it will tell you, because you programmed it in TMC Autotune, what motors you have, what drivers you're using. It will always tell you the drivers, because it can pull that from printer config, the voltage, the run current, and the steps. It can pull all that. It can't pull the motors and stuff like that. These are all your chopper settings, your TMC driver settings. This is good for kind of advanced troubleshooting because you can go in with TMC Autotune, and I think Clipper lets you too. You can adjust this. There is a script out there. Good God, what is it called? Let me see here. It does what TMC Autotune does, but it does it in a different way. I can't remember the name. So many things going on here. I don't remember it. If I do remember it, I'll put it in the description. It's another method of calculating your TMC drivers. And it just takes more time. And from the testing we've done, it didn't show any difference. It gives different values, and you put different values in, and it's actually helped. I believe it helped Andrew make the TMC Autotune better, but it doesn't necessarily change, right? Because you can get to the same way multiple means. So you can try it out. I'll put if I remember, I'll put that in the description of this video. But that's what the top is giving you. This PWM frequency target. This is kind of just the default that's thrown in there. If you're trying to get better performance out of your motors and you've already installed TMC Autotune, the next step would be to start messing with your PWM frequency. You might find that going as low as 20K is going to give you better results. There is a lower limit and there's an upper limit for where it's not going to help and it may hurt. But you can go to 20K and stuff like that, and if you're looking to squeeze, you want more green, you're looking to get a little bit better graphs, you can definitely play with the PWM frequency, and that's something that you can adjust in TMC Autotune. Alright, so back to the main attraction of this graph. It's these two graphs here. We have our global speed energy profile, which I labeled organic, and angular speed energy profile, which I labeled structural. What do? This just gives you the vibrations at your 45s and your 90s, right? X, Y, AB axis. This gives you your vibrations, your motor-induced vibrations throughout the whole circle, the whole unit circle. So this whole thing gets translated into this. And so what do you use for? Your best speeds. If you're printing ABS, you're going to be over here at 125. You want to stay in the green. Stay in the green. If the green's really narrow, you might want to avoid that too. But so if you look at a lot of profiles, they'll use 100 millimeters a second for the speed of your external perimeters. In my experience, it's generally a bad speed to be running at. And this shows you there's a bunch of vibrations. Not a lot, but there's vibrations there. What would be a better place? Over here. Over here. For PLA, you're going to probably be here. You're going to be at, what is that, 195, 90-ish. You're going to be about 90. You may even have to drop down to, 65. Say right here, 65. PLA, you're generally going to be below, for exterior perimeters, below 100, unless you got some really good cooling, and then you might be up here somewhere. So stay in the green for organic, which is shapes that aren't structural, shapes that aren't just like right angles. If they got curves in them and other stuff, this is graph you want. That's why it's organic. Structural, printer parts. This is going to be your graph. You got to choose which axis you're going to be placing your prints in. If you're going to do the standard XY direction, you want the purple black, which is this purple stuff here. That's going to be your peaks. You're going to stay in the troughs here. So 125 would be good for both, right? 100 definitely not good because that gives you your most XY. If you put your prints at an angle at the 45s, you will then be in the troughs of the orange line. So while 50 is a bad frequency for X and Y, it is a good frequency for A and B motors. So you got basically have three graphs in three graphs here. You have your organics, you have your structural. And your structural comes in 0 and 90 degrees or 45 and 135. I don't think most of us actually put our prints at 45 because we want to fill up that bed. So we're going to be purple. If you don't necessarily want to fill up the bed and just want to try and get the best prints possible, try the 45s. You have different speed limits. You actually have a wider range here. Why? Because only one motor is going at a time on a 45. You will have very slight excursions into dual motor, so anything that's off of a 45, so let's say you're running let's draw a picture, make it easier on me. If you are, this is your print, it's a box, you are only at 45, imagine it's a box, you're only at 45s. If you have this, and then you have a rounded corner, and a rounded corner, and you come back here, and you got a rounded corner, and round, right? These round corners from between here and here, you are not on the 45s. You are back on A and B. So, yes, while 125, let's say 100, right? We'll say 100 was good here. 100 is not good here. No. So, even though you're angling them on 45s, chances are you have other angles in there. This is why the 0s and 90s are probably the better bets to go, because chances are you're going to have both motors running. Or if you don't like that, then you go to organic. So that's what this is all telling you. This is your motor frequency profile. There is a means to cancel this out. This is the vibrations caused by your actual motors themselves. You can tell that they're pretty high frequency. They're like 200 and almost 250, I would say. All right, and you got the damping ratio of that. The problem is that this is 1e to the 5. Let's go over here. 1e to the 5. So these ones, in this case, this frequency here, which is going to be over here someplace on this LIS2DW, it's going to be over here, may actually have an effect. But if we go to the this pretty graph here, let's go back. We'll delete that. This graph here, you can see it's 1e to the 5, so it may have an effect because it's going to be over here somewhere. This is your motor's vibration. So you could cancel. Shaketune, there's a branch of Shaketune that allows you to cancel this out with another shaper, a motor shaper, that it applies to your regular input shaper to try and cancel this out also. Or it only really works in Danger Clipper. Or in Danger Clipper, you can try one of the smoother shapers, which is meant to cancel basically everything above 200 hertz out. So it's already effectively going to be taking care of this motor resonance. Now you can try it out. right? You can install Danger Clipper, and you can. It'd be the experimental branch or the bleeding edge branch. It's the bleeding edge branch of Danger Clipper, has the smoother shapers in it. The smoother shapers don't use damping ratio. They calculate somewhere else, in another manner. But you can put. I think they fixed it where you can put the damping ratio in just to put it in, and it won't use it. It won't use that for its calculations, but it can be put in case you want to switch back and forth between regular Clipper and Danger Clipper. You don't got to keep redoing your config. So there is a means to cancel this. It's still in beta. I wouldn't say it's 100% because not a lot of people are doing it yet, and there needs to be a slight adjustment to Clipper to really kind of test it out in Clipper. So I did a little bit. Okay, so we're gonna go back here. I fixed this. Going to do my work. I fixed it. Yay! We're fixed. We're now in the flight path. We've got 000. There was this slight belt induced racking in A, and B was off below 2.0. I retensioned B, or retensioned it, brought it back up. Okay? Fixed it. But what happened here? Right? So this is before, this is after. My Excel was actually higher here, and my damping ratio is lower here. So my Excel's better, my damping ratio is better. Okay, so it's just kind of, this is what I saw, and it's kind of taking you through my troubleshooting process. All right, so this is, as you can see, so why? Before, Excel is 600 lower on this side, or actually on this side before. But now, because I tightened my belts, this little thing started to look a little uglier. And this is, of course, once again, already gave away the secret. It's my linear rail in the carriage. The solution to this is to install a new linear rail, which is why I'm not going to do it because it's still printing fine. All right, so this is another thing. Once you find the problem, you have to ask yourself, is it worth it? Right? Am I chasing good graphs or am I chasing good prints? This one is on my Trident. That's a workhorse for me. It's basically prints 24/7, printing Toys for Tots toys. Also for Toys for Our Nonprofit, which is 3D Printing Elves. We print toys for kids in the Central Valley of California. Any kid wants a toy, basically we give it to them. Doesn't matter the organization. So this guy's running 24/7, right? Right now it's printing Jeeps. And do I want to take a machine down with no visible signs of resonance or ghosting to fix this? To fix the new linear rail, which I know I need, and it eventually will get worse, most likely. But am I going to take it down now? No, I'm not fixing this. It's too much. It's too much work for too little gain. But that's the problem. What else went bad? So symmetry got worse. I got more noise in my belts. It went from this to this because the loose belts were acting as a dampener on the effects of the linear rails, X-linear rails carriage. So, what's the takeaway there? Tighter belts are not always the answer. It would be better for me to fix the issue. It would be better for me to have left it alone. Because I was getting good prints. I did this basically to show you guys. I made it worse. I didn't know it was going to make it worse, but I did this testing to kind of have some evidence on. It's a little troubleshooting technique that I use. But it would have been better for me to leave it alone. As you can see, you want more orange? There's not a lot of purple. Not as good. I made my vibrations worse by tightening the belts. It didn't need to. Prints are still fine. So, and right now the prints are still printing. They're still printing fine. But yeah, it is what it is. Once again, I told you I excited it and moved the tool head. Okay, so that's my little troubleshooting. We're only like 5 hours in now. Common areas for trouble. please explain. Right? We got BFIs. BFIs are a common area for trouble. Why? Because they eat belts. Why do they eat belts? They eat belts because it doesn't matter if it's a V2 or Trident. They eat belts because this carriage is not has too much room for movement in it as compared to the Rama Eilers. So you want everything to be along the same plane. What can happen is you can kink this carriage such that either the bottom is hitting the bearings or the top is hitting the bearings, and it will eat your belts. You need to be careful with this, the BFIs, to make sure that your belts are aligned and going straight through it, and you might need to adjust the angle. You have 2 screws, 1, 2 here in front, or you can see 1, 2. You may need to adjust these screws after you get your belt tension to get that bearing so it's in the same path or same plane as the belt. Other areas for issues is when you fix this gantry. So what you do is you usually do a bed mesh, and in that bed mesh you may see that the rears here are really off. They're either really low or really high. The solution to that is to adjust one of your y-axis. You need to drink some, excuse me. Right? When you do that, you are effectively changing your plane of your y-axis to match the plane of your bed, or vice versa, right? So you're trying to get the bed flat, but you're making an adjustment. You think you started this out with the Y frame equal distance from the X to the top of the frame, and it's you're making it go out of plane to fix any sort of issues in the back of the bed. That can bring an issue in. Not really. I mean, it's something could be solved, but it could be an issue. Right? Let's put that. Umbilicals are always a problem here. It's actually easier to do an umbilical here, but it's harder to get it right, if that makes sense, because you don't have a lot of room to play with. You have basically this much room for your umbilical. And then you're going to have your standard problems. You're going to have tool head issues. You're going to have XY joint issues. You will get a more rigid frame, but it doesn't necessarily translate into better accels. Let me put it that way. So mainly the issues here is what I described. Common areas for trouble here. Not homing and QGLing. You always have to home and QGL before you start doing input shaper on a V2. Other than that, umbilical. Umbilical, number one, by far, umbilicals. If you haven't watched my umbilical video, please watch it. The most common umbilical problem we see is someone coming from here to here, just like this. Even if you put a piano wire in it, it's going to be a problem. Other issue with the Trident and for the V2, super thick umbilical cables, right? You get those the people, and I know why you're doing it. They basically run all 24 wires from the tool head in an umbilical and just go to CAN. I know some people are doing it so that they can run their chambers really hot, and that way they're not going to burn up the electronics in the tool head board. If you're doing that, stick with the cable chains. It's a pain, but that really thick umbilical is hard to get right. It really is. So umbilical is number one. Number two is going to be your XY joints. Screwing, I got pin mod on this. Personal opinion, pin mod wasn't worth it. I've taken it out of a couple machines. Left it in this one because it's working, but if you have a screw right here and a screw right here, it is generally this screw that's going to cause you a problem, and that's making the head of the screw below the plastic. There is nothing between the head of that screw here and the XY joint, the idler here, the tooth idler. And if you screw that in too tight, you're basically locked this up. If you screw basically the screw here and the screw here, and you just wrench them down, your x-axis is not going anywhere. So you want that level. The next thing here is racking. Racking is a big one. There's two kinds of racking. There's mechanical racking and there's belt-induced racking. Mechanical racking is when you set this up and you screwed in your x-axis, it's at an angle. It's just mechanically at an angle. That needs to be fixed, number one. Number two, when you tighten the belts, if you tighten one belt all the way really tight, you have now induced belt-induced racking, because even if you tighten, it's not going to take as many. It may take you, let's say it takes you 5 turns to get this guy in, and you just go 5 turns, 1, 2, 3, 4, 5, and then over here you go 1, 2. You may only see that 3 turns brings you into tension. That's because you've racked it, right? You got to remember that these joints are coupled. If whatever I do on this side is going to be affected on this side, because that belt runs through. So this belt right here touches this x-axis there, and it touches this XY joint here, and it touches this XY joint back here. So the better bet is half turns, half turns, half turns, half turns. And you can sing a song, half turn here, half turn there, whatever you gotta do. Just don't wrench this one all the way in. Don't and you're gonna do a belt-induced racking. And I would actually I would actually think that you should start with the A belt. A belt over here first. Do this belt first, and then come over here, because and it could be whatever I do. When I start with the B belt, I'm always left with a little gap here. So I think if you start with the A belt, try that. See if you're left with the gap here. If you are, it doesn't matter. So those are common areas there. Yeah. V0. This is my nemesis. If you guys have seen me on ask for help on the V0 on the foreign residence channel, and you have a V0, I do not like you. Why is it my nemesis? Because everything is so damn small. Not my cup of tea. Not my cup of tea. All the same issues, except this one adds the umbilical also. As you can see, I'm running CAN bus. Generally, the cable is actually a little short for V0s. It will pull on your tool head. You can go CAN bus on V0, and it actually makes it easier, because now you can make this cable as long as you want. The other thing that's hard is getting the cables right. On a V0, on all the printers, but especially on a V0, it is important to make sure that your belts are the same length, and you have the same number of teeth for both belts on the left side as the right side. There's no going back once you cut those belts. So, because of its small size and its inability to readjust the belts, it's hyper important that you get these belts right the first time, and then you can play with the tension. I call these nubs. So if you're on foreign residence and you're asking for help on this, and I say, why don't you turn a belt maybe half a nub? That little thing right there, that's a nub. That's what I'm calling a nub. Half a nub would be like between there and like here. That's probably about as accurate as we can get on these. So that's the 0. The switch wire. Switch wire. People like to say it's a core XY flipped up vertically. It may be, but it doesn't mean it's that easy to get the belt tension. Belt tension is a bitch on this thing, and it's hard because there's nothing really locking the motors in. There's no other tension. Your motors are your tensioning mechanism. It doesn't have like the front idlers, which would be like up here or something. The motors up here, the front. It doesn't have that, so you can't get that fine tuning you can on a Trident switch wire. I mean, this is maybe a V0, but not. The V0 is its own thing. Yes, it's a Core XY, but it doesn't have the fine tuning, so it's hard to get this guy level. Plus, the belts in the back are hard to tension because it's just a different tension mechanism. So that makes it harder. I would strongly suggest if you get a Trident, a kit, to upgrade to the 9mm belts. I don't like my belts inside the extrusion, which is your standard Voron. Bring them out. When you bring them out, it's actually easier to tension to because you can measure it. Voron's switch wires need two 80XLs, one in the tool head, one on the board. I use a Boxio Provoke 3D accelerometer there. Because I print PLA, the temperature of my bed is lower than the soldering melting point, and the chips can handle. It's like 60°C. I just leave it attached the whole time. I never take it off. There are 2 points to measure with this guy, the bed. So if you measure at the center of the bed, your graph will look like this. That's right here. If you measure here, your graph will look like this. And that is because this bed wobbles. It's got a single linear y-axis going through it, and it wobbles because it's only really held on right here. So everything else kind of flapping in the wind. It's a light PCB board followed by on top of that light frame. If one was so inclined to update the switch wire, I would suggest 2 linear rails here, a double, and a single. Because that will give you more support on that frame, which hopefully means that everything else will be more supported. I'm hoping. I don't know. I've ever run the test. You have your 9 screws here. Here. And so this is telling me, because you got those 9 screws, you're screwing that frame in together, the frame is underneath all this, that it's just not enough support on that black frame, and it vibrates. It does this. It does this. Center of the build plate does this, which is fine if you only print it in the middle of the bed. I fill it up. So that's my 2 cents on common area for trouble. So what leads me to the order of calibration. So, talked with a lot of guys in the different residence channels, unicorn chasing. Thor, talked to Thor about this. Basically, you should do your E steps. Then you should run belt shaper, then input shaper, then vibrations profile. Why? Belt shaper and input shaper will basically alert you to any big mechanical issues. So you want to get, that's why the 0 EI, 5% MZV, it'll take care of any big mechanical issues you have later. Vibrations profile, and they'll give you your acceleration to use, your perimeter acceleration. Vibrations profile will get you your perimeter speed to use. Pressure advance, when you calculate that, it is based upon an interior perimeter, and it's based upon exterior internal speed. Generally, the speeds that are set there currently in like Ellis print guide for how fast you should go are slower than what the printers can actually do. If you're using bamboo or Orca Slicer will set some preset ones in there. They may be too fast, may be too slow. But either way, after you're going to need to adjust them if you don't run it in this order. Then your extrusion multiplier, then print. You can, if you save these for the last, these 3 here, if you put them at the end, all you're going to have to do is go back and redo PA and EM, because you're probably going to go faster. Maybe. I don't know. But you'll have to recalibrate those. So that's the talk I gave. And then this is any questions? Any questions? So Shaketune, this will take you to Shaketune. This will take you to my YouTube. This will take you to AutoTune. This will take you to any of the engineers' website or YouTube channel, which he's got videos on this. This will take you to PF's GitHub. and this will take you to 3D printer and a Whiteboard's YouTube channel. These guys all around have been, well, I haven't talked to Eddie and I haven't talked to 3D printers and a Whiteboard, but their videos got me, kind of kickstarted me into this, followed by talking to Fricks and Andrew and PF. So all these guys, help me make my videos because they help me to learn. So hopefully they'll help you to learn. And this is my YouTube channel, which you're probably watching this on anyway. But yeah, so thank you. And this was the talk I gave of Voron, actually a longer talk. And so have a good night. Thank you, and good night.